I will give you an overview of the SOLTRAC project with which we use low-frequency observations of pulsars to probe the content of the heliosphere. I will first describe what pulsars are and how we use them in SOLTRAC, the instruments that we are using, and the results that we have obtained so far. So pulsars are highly magnetized, fast-rotating neutron stars that generate two beams of emission approximately located on the magnetic poles and that are mostly visible at radio frequencies. While the pulsar rotates, these two beams co-rotate with the star, and if the line of sight of an observer crosses one of the two beams, the observer will see pulsars as a source of periodic emission. The radiation from pulsars undergo to a series of what we call propagation effects induced by magnetized plasma. One of them is dispersion, in which the low-frequency emission from pulsars is delayed with respect to the high-frequency one while it crosses the plasma, and this delay is directly proportional to this parameter called the dispersion measure, that is the integral along the line of sight of the free electrons. Another of these propagation effects is Faraday rotation, in which pulsar emission is highly linearly polarized when it passes, and when the radiation passes through a magnetized plasma, the polarization angle of the frequency rotates, and the rotation can be described as dependent on a parameter called the rotation measure that is proportional to the integral along the line of sight of the parallel component of the magnetic field multiplied by the electron density. Pulsars are fast-moving objects, and so the line of sight of the observer changes constantly to follow them. And given that dispersion measure and rotation measure are dependent on the line of sight, also dispersion measure and the rotation measure typically varies with time. So in the SOLTRAC project, we are exploiting the fact that DM and RM that can be inferred from pulsar observations give us a handle on the electron density and the magnetic field of the plasma. And we are exploiting this property to study the electron content and the magnetic content of the solar wind. In particular, we use observations of pulsars to generate electron density and the magnetic field profile of the solar wind, and also to study coronal mass ejections. The propagation phenomena, so including dispersion and Faraday rotation, are inversely proportional to the observing frequencies. And this is why such effects can be measured and studied very precisely when using low-frequency observatories. This is also why we are using, for example, LOFAR, the low-frequency array that can observe below 250 megahertz. But for this project, we are using the subband between basically 100 and 200 megahertz. We are not only using the LOFAR core, but also the international stations, and pulsar monitoring observations have been ongoing since 2013 for more than 100 pulsars with a weekly to monthly cadence. Another observatory that we are using is NenuFAR. That is a low-frequency interferometer located in France that can observe below 100 megahertz, and also their pulsar observations are ongoing since 2019. The first result that I want to bring up today has been published in a paper earlier this year. In this paper, we have collected data from the pulsar monitoring campaign since 2013. And we have selected in particular pulsars that are located very close to the ecliptic. And we have obtained the dispersion measure time series that each of them searched for solar wind signatures after removing the interstellar component. Of all the pulsars that we studied, 14 showed solar wind signatures that are shown here. Here you can see in black the DM time series of each of the pulsars, and in red the DM time series during the solar approaches. And one particular feature that we have detected in this study was that some pulsars for the first time were showing signatures of what we think is the solar cycle. In particular, for example, some pulsars are seeing decreasing the amplitude of the signature of the solar wind, passing from the solar maximum to the solar minimum. Other pulsars, especially the most ecliptic ones, are not showing the same feature, and this is currently under examination. Another work that I want to mention has been published in Solar Physics last year, and it is the software CME Chaser, with which we determine whether a specific observation of an astronomical object that can be a pulsar or another object was affected by the passage of a coronal mass ejection. With this, we are also carrying out a search for CME occultations in the pulsar observations with LOFAR and NenuFAR, so that we can also isolate specific observations that have been affected by CMEs to study the properties of the CME themselves. The third work that I want to bring up has been recently submitted, in this work we have searched for frequency-dependent DM. So the DM, the dispersion measure, is not usually frequency-dependent, is a frequency-independent parameter, but in case it is showing a frequency, a dependence on frequency, it means that other processes play the role during the propagation in a certain medium, in particular turbulent effects. So we have obtained a simultaneous data set on this pulsar 1022 plus 1001. That is a very, very ecliptic one with LOFAR and NenuFAR, searching for frequency dependent DM, and indeed we have detected it exactly at the closest approach to the sun, marked by this gray line. You can see here the discrepancy in the DM between NenuFAR in red and LOFAR in black. And we have simulated the geometric delay induced by turbulent processes in the solar wind to see if they could match the feature that we detected, and indeed there is a very good match for the two most extreme points that shows discrepancy. And in the future we aim to apply this finding to estimate the inner scale of the solar wind turbulence. Other two works that we are carrying out now are related to the validation of software that can simulate the conditions in the solar wind in 3D, such as IPS tomography and EUHFORIA. What we are doing is to simulate the conditions of the solar wind with these softwares, including the distribution of particles and free electrons. In the reconstructed volumes, we are piercing the reconstructed volumes with the line of sight towards our pulsars, and we are integrating along the line of sight in these simulated volumes to obtain the column density that is exactly our DM, and we are comparing it with our DMs. Here I'm showing 4 solar passages of 2 different pulsars, JO34-0534 and the already mentioned 1022. In black you can see the reconstructed tomography, IPS tomography, for example, and in red the pulsar data, and you can see that except for some clear discrepancies, the agreement is extremely good. And we are also carrying out the same work with EUHFORIA, that has a completely different approach with respect to IPS tomography that is based on interplanetary scintillation measurements. EUHFORIA is a semi-empirical MHD software used also in space weather. And currently this work is ongoing. I haven't mentioned until now works on Faraday rotation. The rotation measure that we can determine from a pulsar observation is given by three components: the interstellar medium, the solar wind, and the ionosphere. While, of course, to obtain the rotation measure of the solar wind, we need to subtract the interstellar medium one and especially the ionospheric one. The interstellar medium doesn't pose a problem because it is very constant, but the ionospheric contribution is extremely variable in time and space. And this is the main bottleneck to RM studies of the solar wind to date. As an example, I am showing here the RM time series towards the already mentioned 1022 plus 1001. And you can clearly see that overimposed to the RM time series of the solar wind, there is this clear sine wave that we know, of which we know the origin. So the RM that I'm showing here has been already subtracted of its interstellar, sorry, not of the interstellar medium component, but of the ionospheric component, as we can predict it with some cutting edge software such as RM extract from Mike Mevius. But what we see, so this wavy signature is clearly a systematic left by the software. As I said, we know that it is a systematic because of a study that was carried out in 2019 by Poraico and collaborators, in which the authors studied the effectiveness of the combination of various total electron content maps with geomagnetic fields in the correction of the rotation measures that we can obtain with pulsars. And indeed, the authors reported two kinds of systematics left by the ionospheric corrections. One is this daily sine wave that we also saw in the previous plot, and the second one was a monotonic trend, a monotonic increasing trend with time. So recently we have been working quite intensely with Mike Mevius and Natalia Poraico to substitute one of the main assumptions of the software that we had used in Poraico et al. 2019. That is the thin screen approximation. That is, we in RM extract, the ionosphere is approximated as a thin screen, and we know that, of course, this is not correct. So recently we have substituted the thin screen approximation of the free electrons in the ionosphere with a full profile. This was extremely helpful to take care of this monotonic increasing trend that we saw in the work presented in 2019, but the daily sine wave is still present, and of course this is a main problem for solar wind studies, as it has of course also has an harmonic at 1 year. So the next step is to implement in RM extract to substitute this full profile of the electron content with the tomographic data of the ionosphere that are being provided to us by the UPC group in Spain. And we hope that this will take care once and for all of the daily sine wave. And this is all. Thank you for the attention.